Good afternoon. I'm Davide Poli. This is my fourth doctoral meeting. And I'm going to present to you my thesis on 2D fluid modeling of Hall-effect thruster discharges, supervised by Pablo Fajardo and Eduardo Edo. So Guillermo explained most of the things already, but what I'm aimed to study in my thesis is the problem of the anomalous transport. So the onset of instabilities that creates this enhanced electron mobility can't be explained by collisional theory, and the end effect is that we have reduced magnetic confinement. This is in most of E-cross-B devices a loss of performance. This can't be explained with classical collisional theory, which means that at the moment we don't have predictive models of Hall thrusters, which means that we rely on scaling laws to design new prototypes. The methodology that I applied in this thesis is the development of one-dimensional, two-dimensional, time-dependent fluid models to characterize the onset and saturation of these instabilities. As you can see, as you've just seen, particle in cell code are commonly used in the E-cross-B community to study this kind of plasma. So why would anyone bother with fluid models? Well, fluid models deal directly with macroscopic quantities with which we are more acquainted. So they're easy to interpret, and it is also much more flexible because we can turn on and off certain kind of source terms, so we can include more or less physics and isolate the effects inside the equations. And they can describe many instabilities because, as we've seen with Matteo Ripoli, there's many fluid formulation of local instabilities in E-cross-B plasmas. On the other hand, we lack non-Maxwellian effect because we are bounded to quasi-Maxwellian velocity distribution function. We lack kinetic effects, and we usually rely on delicate numerical algorithms. Depending on the technique that we're using to solve the equations, we are also subject to numerical diffusion. Nevertheless, the combined use of particle in cell simulation with Guillermo and fluid simulation can narrow down, excluding the effects, kinetic effects, fluid effects, to narrow down the triggering mechanism of these instabilities. In the previous year, I've presented my one-dimensional models. I've developed essentially two of them. One is quasi-neutral, one is non-neutral. They're based on the same framework. They are time-dependent, and they simulate the axial discharge of the Hall-effect thruster. They've been used for resolving axial instabilities, to perform parametric studies, and to assess performance, to do performance analysis of Hall-effect thrusters. These results have been published in 2 journal articles. Just to sum up here, we can see some of the results that I've obtained with these models. For example, we can see on the right the non-neutral model that resolves the so-called breathing mode oscillation, this strong predator-prey or ionization instability. We can see that we have fluctuations in the ion density, we have fluctuations in the current, and so on. On the left, we can see with the quasi-neutral model, which is inherently faster, we can see one of these large parametric analyses I was talking about. Here, for example, is the onset of the breathing mode instability by changing 2 parameters, namely the magnetic field profile inside the channel and the neutral wall collisionality. Going now on the development of the 2D model, in the years I've developed a finite volume based compressible fluid solver parallelized with MPI to solve the axial azimuthal plane of a Hall thruster, which is that red dashed line in the Hall thruster picture from Busek. Of course, I'm not going to resolve the whole circumference because it's very large, but just a small portion with periodic boundary conditions. This simulation includes a 3-fluid model, includes full electron inertia, non-neutral effects, and neutral dynamics, which means that, as we saw before, there's an extreme scale separation between time scales, spatial scales, which make this simulation extremely difficult and time-consuming. These are, for example, the last simulation that I ran. On the right, you can see this very complex picture. There's many plots. In the top left, we can see the azimuthal electric field. So we have instabilities, we have turbulence. In the plot below, we can see the time evolution of the plasma density, the electron density. We can see that at a certain point, it grows, and this is due to the onset of the breathing mode instability in the axial direction. So we have interplay of axial and azimuthal instabilities. This simulation is heavy. It's 500,000 cells for 52 million time steps for a total simulated time of 150 microseconds. So this video is a speed up of the real simulation of 200,000 times, more or less, of what happens in reality, and took some 42 days to simulate. So quite substantial simulation time on only 30 cores, because that's what I had available. But nonetheless, we can see that we have transport. We can see, for example, on the left plot, the blue line is the Hall parameter, which is essentially how much electrons are magnetized and confined, more or less. The orange line, instead, is the one that, abusing the notation, we can say effective Hall parameter, so the ratio of the velocities, which means azimuthal and axial velocities, which means that since it's 1 or 2 order of magnitudes lower than the collisional one, we have extra transport that the collisions cannot explain. So we saw something also that is not expected, which is the onset of another axial instability called ion transit time instability. This instability shows both in peak and fluid models as a strong, in fluid much stronger and sudden, shock in the axial ion velocity. It is, in the literature, usually it is correlated to a lack of anomalous transport. For example, in my simulation, I use a vacuum permittivity which is 25 times larger, so it's more relaxed, the instabilities are more relaxed. Maybe that's the reason for why we don't have enough transport. I'm honestly not sure about this. But the interesting thing is that I recovered this strong shock, which has actually the same exact shape, in the two-dimensional code on the left, and in the quasi-neutral code that I developed in the first years on the right. The plume is more extended, but you can see that the shock behaves in the same way when I reduce the anomalous transport. So there's something going on there which requires more attention. Ion transit time in the literature was never studied much because it was never considered very important. On a second, let's say, on a parallel branch, I'm continuing a work that I started during my research stay in Laplace, at Laplace in Toulouse, Laplace Laboratory, which is the simulation of a penning-like device. Penning devices were created at the beginning of the last century. They span a broad range of neutral pressures, magnetic fields, and as you can see in the plot on top from Schurman, there's many modes of operation which are associated, as you can see in the bottom plot, with a violent or sudden mode transition in the cross-field transport. So we have many instabilities developing, and we thought, okay, we can try to understand this and to study this because it's conceptually simpler than a Hall thruster. For example, the magnetic field is constant, so, and uniform. That simplifies things already. Turns out that this is a difficult simulation from the point of view of numerical modeling because of the existence of near vacuum states, which for fluid approximation is not ideal. Nevertheless, what we're doing now is simulating a mode transition of plasma instabilities, which is something that has never been done before, maybe once in the literature with a peak code, never with a fluid code. So I started from the extreme of the neutral pressure, which is no neutrals. So we go towards a pure electron plasma, as you can see. Well, you can see, but it's a pure electron plasma. And as you can see on the right, that's my code, the time evolution of the plasma density, of the electron density, which features the onset of a strong diachotron instability. We can see that it's like a Kelvin-Helmholtz instability, but in E cross B plasmas. We can see that we have the breakdown of this shear layer in vortexes that then merge and are convected around. And this is remarkably similar to these pictures of an actual experiment that has been carried out. And this is actual photographs of these electron vortexes that are merging around and being convected. So this is working well, and we're happy about this. When we increase the pressure, however, we see a mode transition, and we're happy because this is what we were looking for. And we have the formation of what are called spokes. In this case, it's a mode larger than 1. We can see that we have counter-streaming spokes. Why do they form? It can be many reasons. For example, modified Simon-Cohen instability, critical ionization velocity theory, or drift dissipative instabilities. We're still analyzing this. Indeed, this mode transition occurs in our simulations by increasing the pressure. We have a more or less complex picture. For example, in the bottom left plot, we can see that increasing the neutral pressure, we have a maximum in the current that reaches the wall. And we can have a change in plasma potential from very deep potential wells to positive potentials. It's a complex scenario. We're still analyzing these. We want to see what happens at larger magnetic fields and what trigger the spoke transition. Extra activities that I've done this past year is completing the research stay, and with Matteo Guaita, I've upgraded the numerical resources of the group. We've purchased, designed, installed, and we taught people in our group how to use the new cluster. And well, next steps are the Fluid Mechanics Conference at the end of the month, IPC if they decide to send the acceptance of the abstract, and well, publish these last results and finish the thesis in the upcoming months. These are my contributions between conferences, future conferences, and the two publications, and I'll answer any question.